like it. I would love that one. You're the one who looks like mirror.
I smell that marker all the way over here.
It's not the marker.
Getting high.
The education.
Oh, multiply.
People said do something a little more tough. So I'm doing something a little more tough.
But this is tough for the hardware.
What's that?
The multiplies is tough for the hardware.
Shouldn't there be another register in the multiply line? Or I don't know how multiply works.
That must be it. Because I guarantee you this is correct.
Okay.
Oh, okay.
Let's see.
What does that say? No flow? End flow? What the heck does that mean?
You don't know what end flow
That means somebody did not tell you how multiply works.
You don't know multiply low?
That's what that means.
I didn't know we had multiply built in.
When you multiply, your result's going to be bigger, so you have to split it. That's why we have low and
Somebody
high.
told you how it works.
I read it, so that's
And what?
Yeah.
So it's low and high output from multiply.
Just go get your food. Stop sharp.
Yeah, I'm going to go get food.
Okay, get me some too.
Okay, I said I wasn't going to give you an intelligence, but I came up with an idea.
Wow.
Now, somebody can tell me what this one actually does. I don't have one command before and I don't have one command after. Adding two commands into this does something intelligent. If you can tell me what it is, I'll give that person an extra credit. Make this okay. This is
Fibonacci numbers.
we have a guess.
So multiply. What does end flow do exactly?
It's the rest of multiply. Multiply multiplies these two ones, and it sticks it in a two-register combo called high-low.
Okay.
Because when you multiply two things, 9 times 9 is
81.
81. It took 2 digits, didn't it?
Okay.
Right? So when you multiply numbers, it takes twice as many digits potentially to hold the answer as your starting
high
point.
and low.
Right? So since I've multiplied 2 registers, I need 2 registers to hold it. So they just always stick the result of multiplying high-low.
Oh,
When you do
okay.
division, you load, in essence, your answer actually goes to high-low as well. You take 2 registers, divide them, you get the quotient and the modulus. So I went to the 2 different
5
things.
times J.
Modulus quotient. So,
Let's see.
you always use high-low for multiplies and divs. And then what you do is you have 2 commands. Since this is not normal register index, right, they're special purpose registers, I have to have a command to access those. Move from low. It takes the result in low and moves it to R6.
Now, what
So what
does...
this means is multiply 4 and 5 and stick the low 32 bits into R6. Which, as long as your number is sufficiently small, that's probably your normal multiply. Because this is true as long as your multiplication didn't result in anything bigger than 2 billion. 4 billion.
So does it add the remainders of an array?
And then it.
So this essentially, when people will give you like a shorthand notation, and they'll say multiply R6, R4, R5. They're technically wrong. It's actually this. This is a shorthand, and this is only correct if your numbers are sufficiently small. Right? If you understand this is what's happening, I can actually test to see if this is right, so that I can give you an error if it's not, and you can deal with both high and low. So you can deal with big hits.
on the add, R7, R6, we don't need another register?
No, I do not.
Maybe 7 plus 6.
So are you adding the remainders of an
Oh,
array?
so you're right. No, I do. Thank you. Yes, that one I did actually. That's a goof on my part.
2 extra credit points for me. Okay, so we add...
Should be an email. You got an error on mine. That's good. I'll take it.
Hey, I was
You should be an error. Well, that's,
Hey,
you gotta say, I only take one slam from there.
yeah, got your opportunity.
Gets credit, so you should want to slam me.
Are
Okay?
you multiplying 2 arrays?
Not arrays.
No,
Well,
he's adding the remainders of an array.
okay, so hold on. So
You're getting the sum.
6
you're putting it in
times
an offset.
30. Now if I
Nobody's
take
got
30,
it.
if I take
Hold on,
30.
hold on.
Wait, this is. It's a math
There's a
function.
store.
It's a sequence of numbers. It's geometric. Oh man.
Yeah, cut it off at 10 after.
I feel like we did this in 535.
We did.
Oh man, you're making me cry, Dr. Schubert.
What's that?
You're making me cry here. Oh.
Michael.
No, because R1 is your loop index.
Okay, so 7.
R2 and R3 jump
So
to
take
the right.
my multiples, add 6, and then
Or there's
store
vector
7.
map.
And take. Okay, hold on. So 0 times 1, that's 0. 0 plus 0, 0.
He said there's 2 lines missing
2.
from this?
Assuming you want it. Well, there could be, I mean, there's a bunch of stuff in setup up above. Okay.
Oh.
Setting up R2.
Oh.
Yeah.
I have to initialize some of this, so that stuff is missing up above. And there's
The load
one
has
line on a
remainder.
single one at the end.
Alright, and then what's the next one?
You said the low had the remainder, right? For the multiplication.
On the lower side.
Well, high and low have the result, but assuming that the numbers weren't big, this has the first 2 billion digit-wise, and that's above 2 billion. Well, actually, if it's unsigned, you call it 4 billion. So depending on whether you're signed or unsigned, it's got 2 to 4 billion in it,
Oh, okay. So it's
right? So as long as the result of your multiplication is less than 2 or 4 billion, signed or unsigned, then it's here.
Does
If it gets
this-
above that, it's in both.
Does this build Pascal's triangle? No. I'm out of ideas. Because I know what we're doing
10
here.
seconds.
Oh, there after 10 minutes.
No, I said when it gets to 10 after, I'm gonna cut this off, so we don't.
multiply the numbers and you add.
That's why the lower part of the
array elements in your island.
I am, it's called an inner product.
Oh my god.
2 vectors, I'm walking through them, I multiply the corresponding elements, sum them up.
Are we doing dot product? Is that what it is?
Inner product
That's
of
a
2
remainder.
vectors.
That's a
Is it-
remainder.
is it
because
dot
the low
product?
remainder.
But it's an inner product of 2 vectors.
I see. We're close.
I thought of that.
Yes, that is true, a lot of people said vector, but that's not sufficient. There's a lot of things I can do with a vector. Inner product is only one of them. You know, if I make R2 and R3 equal, it's called a norm, okay? So, you know, all kinds of fun stuff I can alter with this code. Okay, so we've got a piece of code that does something. Now, we want to take this and we want to schedule. Let's assume that there is a delay, because I've got a lot of hazards. So we should locate the hazard, and we'll say, from a load to its use, let's say there's an extra 2 cycles of latency. Let's say from a multiplication to when it can be used, let's just say it's 1, just for the sake of argument. And we'll assume everything else has no, delay as it goes. We'll assume we've got a predictor and it's a good predictor, we trust it, and that the adds finish in a cycle. Fair?
So it's technically 3 cycles after your goal, you can use that information. 2 cycles after your goal.
Well, this is a delay of 2, so instead of going to the next
Okay.
thing, you have to have 2 no loops. Right? On this one, between a multiply and when you can actually access the result of flow, there has to be at least 1 no loop, or one other instruction that's not using the data. Fair?
Okay.
Okay. So this is a loop. How do I know it's a loop?
Because of the branching.
The branch is up. Branching up, loop. All right, so now I want to schedule this thing.
Well, we
You
want
have to tell me, 1 or 2, 3 processors, how many processors do I have?
3.5.
Let's call it 3.
3
300.
processors.
300.
300.
That's a lot of, if you really want,
That would be
at that
like.
point I'm gonna go home, write a program, just to roll a whole bunch. Okay, so I got 3 processors.
So let's write a loop to unroll this loop.
I already care, I'll go home, I'll write the program for you.
Dude, I was doing this email before. So weird.
Okay,
I just didn't want to say anything.
so I need to
Because I
know
said, what
what,
was he last time?
to show my hazards, there's several ways I can show hazards. I can write on the lines what the hazard is, I can draw a picture.
It's right on the line.
So, my honest opinion is that it's easier to draw the picture. I mean, it's up to you on what you want to do, but I'm a visual person, particularly if you're in a kind of pressure situation, it's easy to miss something. It's harder to miss when you draw a picture. So, I'm just going to label these. This is instruction 1, 2, 3, 4, 5, 6, 7, 8. So, any dependencies between 1 and 2?
No.
They don't even share a register.
All right.
Right? Okay. How about 3 and anything before?
Yeah.
Yeah.
Okay. Both 1 and 2. What type of dependence?
Read after write.
So read after write. This is a true data dependence. How about 3 to 4?
No.
Yeah.
3 to 4?
Yeah, you need to multiply and get the
Oh
result.
yeah.
Implicitly, the extra field here is high, low. And implicitly, there's an extra field here, low.
That's a true data dependent.
Source, destination. Source, destination. This is a destination. That's a source. So I'm reading after a write.
Right.
You have to know it's implicit in the command. This multiply writes to high-low, move from low, reads from low. So this one's reading low, that one's writing low.
Read after write.
So it's a read after write.
It's a raw
That
error.
one catches a lot of people.
Well, yeah, because you go through real quick, like, oh, those are R5 and R4
Yeah, a
and
lot of
R6.
people check those. But that's why it's good to know. Not all dependencies are explicitly written.
Oh dear.
How about the 5?
5. Yeah, it's a
What type?
name dependence. No, it's a true data dependence.
Yeah.
Oh yeah, because it's
This one
a
writes the 6, this one reads 6.
It's a write after. It's a read after write.
It's a read after write, true data dependence again.
How long is the high and low like available for? Should you wait?
Until somebody else overwrites it. So another multiply or another div command comes in. So that's actually when you do division and you also get a modulus, it's actually much faster. Your first div command, right? You actually give it and you say, say div, whatever, R1, R2. Right? Those are the two that are being divided. If I do a move from high, I'm getting the quotient. I can then do a move from low, and I've got the modulus. I calculate ones, I get both results. And it's just which register do you pull from. So if you ever look at the algorithm for doing division, it generates both automatically. That's the one that's shifting to the right. And so what shifts to the right ends up being the remainder. That's why low ends up with the remainder, high ends up with the quotient. It's shifting in the quotient base. So yeah, it lasts for a while. We use that. You also use it when you're doing videos and stuff like that, for larger than your data size ones. How about 6?
I don't know, 1, but a long time ago.
Okay, in what way?
Name dependence.
It's only in name.
How is? Wait.
How about
Oh
7?
yeah. Same thing.
Kept on. 2. All right, how about 8?
No.
How about 9?
8.
It's a true data dependence. Yes? Actually,
Yeah,
so you
right.
missed an opportunity to kill me, but I got it.
I just.
Actually, Dr. Schubert, you should have gone to the top.
Too late. You have to catch my errors before I catch my errors.
Darn self-correcting code.
Yes.
Okay.
Okay. Do we feel good about the code as it goes on?
Yeah.
So there's just one more thing I would add on, which is just the.
So why is the R1 at the same, I'm sorry, 8 at the same level as 4?
Right? Because I didn't want to draw that long an arrow. Does that make you happier? And we should let 8 actually be even cooler.
It's the boss.
It's the ultimate
Yeah.
construction.
The 8 ball.
It's the 8 ball.
Yeah. And now we stuck it in the corner pocket. Okay. We feel good with this?
Yeah.
Okay, so what I would note on this as I'm going through is, if I've got latencies on here to remind myself, I just put the latencies in. +2, +2, +2. Right? These are loads, it's being used, this is a multiply, that's when you're accessing load. So now I have, this was a directed graph, right? This is a DAG, this is a weighted DAG, right?
DAG. Directive acyclic graph.
Technically, there is a cycle outside, but we've split it. So this is just inside the loop, and it cycles on the outside.
And 9's the control line right there? That's the control.
Yeah, I put that line across just to remind myself that's the one that has the control. Technically, you don't need that, but without it, then you always have to keep remembering where the heck is the branch. So that just reminds me, don't move anything past this line. So that's my own, like I said, it's my own weirdness to it, but it has helped in the past. All right, now I want to fit this in. Am I going to be able to fit this in efficiently?
No,
Why not?
because
Huh?
because there's 3
We got
processors.
1, 2. All right, I got 3, 4, 5, but I can't use this immediately. I gotta have 2 no ops. All right, 3 no op, 4, and then 5 can use it immediately, which means 9. I'll just stick 9 on the far side just to hold stuff. So I'll put 9 in there. That means, in this case, I can't do any better than something, it doesn't matter where 8 is at that point. Yeah, a lot of blank fields, don't I?
Yeah.
How many blank fields?
1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 blank fields.
14. So I've got 14 empty fields, right? Which means I'm only doing 9 out of 22. It's not a very high efficiency.
2, 6, and 7.
Have I not say where's, oh, so I can get there by 2. Right? But that's, right, so I can stick those anywhere I want.
Yeah, this is just name.
Right. So I got 3 times 1, 2, 3, 4, 5, 6, 7. All right. So 9 out of 21 is not that impressive, is it? All right. So now we want to unroll our code and see what we can do on this to make it better. If I unroll it once, can I get perfect efficiency? No, why?
Because we'll still have no ops over
I
there.
have 12 spaces I have to fill.
Right.
That's assuming I don't add an extra line, but I will have to add an extra line. So that means, in essence, I'm going to run into a problem with just not having enough. At 3 might I be able to? Yes. All right. Well, I'll have to at least add one more line here for, like a 9A and a 9B, right? And I can put their appropriate 8As and 8Bs here, right? So I'm going to have to add at least 2 more lines, which adds 6 more potential commands, right?
All right.
So I will have gone from 21 to
24. It's 27.
27
27.
slots. 21 plus 6, 27. So I've got 27 slots. I've got 9 commands. Everything works out perfect. How many unrolls would it take for 9 to fit into 27?
3.
3. It's 3 unrolls.
Right.
So if everything goes perfectly, it'll work.
But
Right? If things do not work perfectly, right, then we blame Avi.
oh, we blame me? What?
I don't know how long it'll take for that one to come down. Okay, so I obviously have to move a lot of things past the line, don't I?
Yeah.
So on each of these subsequent iterations, my registers are going to run into some issues, aren't they? Right? That's going to be my big problem as it comes down. Now, are there any registers in here that I cannot rename to get rid of conflicts?
All the
R2 and R3.
no, those ones we can because those are
I
just
can actually take care of that problem fairly straightforward. Let me just move 6 and 7 out. All right? I can do a 1A, 2A, or I guess I'll call them B and C. All right? A, B, B. I can do that fairly easy, and all I have to do on here for 1A is just load R4. And notice I'm getting a -4 here, is what I have to do to it. And 2A is just load. Now these numbers are where my problem's going to be. But realize for the second unrolling, if I pull this up and I haven't updated R2 and R3 yet, I can blow them away, can't I? Because I don't need it to actually be updated.
right.
Because I do the effect net 4 -4 of it there. What would I do for the B version?
You would increment by 4.
-8.
Oh, -8. Okay.
Right?
Right, because you need to go.
So I can take care of that without too much trouble, can't I?
All right.
And that might even allow me to save, because I really only need, for the whole block of unrolls, I only need to do these once for the whole block. So I can actually cut a couple commands. So that's why I can, remember we talked about you can get beyond the actual efficiency that's possible. I won't, again, I'm not going to do that here. I'll do the A's and B's explicitly, but realize I can actually get better than theoretical because I can delete commands. All right, so that's fairly straightforward. The only issue comes in here, right? This command will overwrite R4. I, in essence, have what type of an error? Right after right. Remember those problems we said that it comes in strange things when you start moving your code around?
Right.
So what do I have to do?
Rename. Or no, undo.
Rename it.
Or okay.
All right? The highest register I use is R7. R8, R9. Which means my multiply, 3A, has to use 8 and 9 now, right? Any issue there?
No.
No, I've just taken care of that problem.
Right.
Now, if I have multiple multiplication units so that they can happen at the same time, I'll have different moves from highs and lows. Right? So that will depend on where that unit is coming from as it's going on. I'm going to assume I have a different one on each pipeline. So as long as I start a multiply in a different pipe, they won't conflict. It'll be a high and low per pipe. That's a fairly standard setup. Huh? Okay, so I have no problems then at high-low because I'll just stick, as long as I make sure 3A and B are in different areas, there's no worries. Okay? So all I have to do is just put 1A, 2A, 1, 2 blanks. I can put 3A there. Now, gonna move my 8 because 1b, 2b, 1, 2, 3b. Need to get to multiply there. Fair enough?
Yeah.
All right. I didn't actually stick these in spaces, did I? 8A, 8B. Okay. How about 4? Does 4 need to be changed to the A version?
Yeah, 4 and 5. So,
4 writes to R6.
Right.
So if 4 writes to R6, the first time I'm going to have this available, I'm going to actually have to move my 8A somewhere. I'm going to move it up 1 so I can get 4A. Does it run into a problem with R6?
Yeah.
This one needs R6 and it reads R6. This one writes to
R6. Yeah. So we have to move that one down after the 5.
Why is this one's R6 value is good at the end of this cycle to the beginning of this cycle.
Okay.
It's all right after read.
This one, when it writes, it starts at the end of its cycle. Is there a conflict?
No.
Not as long as I keep it here. If I move this one up further than that, I'd have a problem, but I'd also have a latency delay problem of getting it. All right? So remember, I can be taking one value out and shoving another one in. Here I'm sticking it in and I'm pulling that one out. That's no problem. It's that whole doorway problem, right?
Right.
Somebody can be going out while somebody's walking in. It's just a continuous line of them. If this moved up to here, I'm screwed, right? It's got to stay there. It cannot go start-wise faster than that. This one cannot start until this one is being read, but it's not. So I don't have to. If you were paranoid, you could actually change that. And yeah, I just increment the numbers and stuff. But realize I don't actually need it here. All right. Now what? Okay, so where can I put 5A? And does 5A need to be different?
No.
No.
So I can just stick 5A here, can I?
Right.
They're using the same registers, they just have high-low different. But in this case, this one's going in from here to here. Right? Red here, use there. No worries. All right.
No, we need 4B and 5B.
Okay, so where does 4B have to go?
No.
It has to go after.
Yeah, let's go where this 9A thing is, right? So I got to move 9A around, which means I have to move it to 8B, which means I got to do 8B earlier.
So move 8A up earlier too.
You know, well, there wasn't a need for 8A, too. You could if you wanted. As it's going on. All you're doing at the end of this is you're decrementing a counter, right?
Yeah.
So you just have to make sure you don't conflict with anybody else's counter, or you make your destination a different thing. Right? And then I could just have one jump all three. As intermediate results, whatever makes you happy. But in this case, if I want, I got to make sure that I don't end up getting the wrong value sent to somebody else. That's the big check I've got to make sure I don't get. Right? So on these ones that come in, right, if this, as it's going, 8A at the moment, we haven't actually checked those. Right? So I'll leave the 8As and B's off because we're going to have to fit them in. We will have to do a little manipulation on them. Okay. But we can fit them. So B, 4B has to fit here, doesn't it? Yeah. To grab the low in that category. And then that means my 5B has to be here. Does 4B have to be changed?
No.
The same exact reason that 4A did it. This one is reading here to there. This one's going here to here. None of them overlap in time. So they're all golden. I don't need to redo them. Okay? Okay, so I've gone up to 5B. How about 6? Oh, actually, I didn't ask you. Do the 5s have to change anything? Clearly the 6s didn't. But do I have to change R7?
No.
No, why?
It's not dependent on anything.
It's a running sum. I want you to reuse the number. Right? That's the whole point of a running sum, is it better hit everybody.
Right.
So this one just adds in the first number, the second number, the third number. You get all 3 numbers in. So no worries. So that's perfectly fine. So 5 is good. How about 6?
Yeah. Now that we're already doing the -4, we have to change that.
I can squeeze stuff in now, can't I?
Yeah.
All right? Let me not worry about the 8s here because we have to move them around. All right, I got 1, 3. Make sure I note my spots. That's got a spot here. Got one there. One there. Okay. Just don't want to lose one of my locations that we have to fill in. Okay. For these ones, this is where I can go to hyper efficiency. Do we want to try to go higher efficiency than normal, or?
Yeah.
Okay. So realize what I can do, since I've already taken care of these kind of blocks and I'm only using them for addressing. I'm not using them for the loop index. So they only matter for the next time I come through the whole loop. As long as I don't modify R2 or R3 before this point, they won't interfere with anything. So I can just jump 3 memory locations down, which would be what?
12.
Minus 12. So I just do a -12 on 6 and 7, and I don't need an AB. Because that jumps the whole block of 3. I've got a huge array, and all I'm doing is I'm doing pointers to blocks now. Before in your code, you were stepping down each one. Now what I've done is I've blocked them into groups of 3. Right? And so I've got a pointer to each of the blocks as it's walking down. And then you just do offsets. The 0 offset, the -4 offset, the -8 offset. Just doing it a block at a time. And I just move the block pointer. So instead of having to move individual ones, I just move the whole block. It's analogous to what you do on a stack, right? Right? You have a stack pointer, but you also have the entire block that's on your stack. So, okay. So what we've got on here, I can actually modify this and just do the whole thing. And now I don't have to do the AB part. But now I've got to make sure 6 and 7 now have to have a right conflict with the ABs that go on, which means I can't do them before this instant. So, I mean, I can do them here if I feel like. I can go 6 and 7. I can do 6 and 7 here if I wanted. I can do 6 and 7 next to each other. The only thing I can't do is I can't put a 6 and 7 here. I can even stick 6 and 7 there. No worries. We good?
Yeah.
Okay, so we look at that and we go, okay, now I have to do the 8s. The 8s, A, B, and C is potentially going to run into some issues now, right? Because now I'm doing, this is now an index counter. Right, but now I'm doing blocks at a time. But I need to find out if I leave early, right? Because I go to a whole block. What if I only want that first one? Right? Well, that's what the 8A is calculating. Should I exit after the first one and not do the update for the second and third, and so on. Okay. So, of these ones, R1 has to be pointing at the overall problem, doesn't it? So is that block or individual? Which one should update it? 8, 8A, or 8B?
8.
Because I obviously have a name problem if they all update it. Right? 8 is going to go one step at a time. 8A has to do 2 at a time. 8B has to do 3 at a time. Do we agree?
Yeah.
That's what's going on. If I do them in sequence, I don't have enough time here because I don't have commands down. If I could just go 8, 8A, 8B, I'd be fine. But I don't have space there to actually calculate them. So I have to calculate them early. That means if I use R1, it will be overwritten by the time I get to 9. I've got a name problem.
Right.
You agree?
Right.
Because it's right after right. So I can't do 8A, 8B, or 8, 8A, 8B unless I change them. They can't all use R1.
Right.
So who gets to keep R1?
8B.
Now have call for 8, for 8B. Anybody want to go for 8A? Well, good. 8A is wrong. There is a right answer. It is one of these two. You want to make an argument for 8?
Was there since it's the first one, it only needs to jump to the first block.
Okay.
So,
Want to make an argument for 8B?
Yeah, I'm right. Nah. Well, because we only have to go to the top once we reach the bottom. Otherwise, we can just fall through.
Is anybody persuaded by either?
If you go too far, then there aren't that many elements left.
What if you do go too far? Isn't that why we have different things? We turn 9 into an exit to loop. Right? And you haven't updated the running sum yet for the next one. You've loaded it, you've calculated in the multiply unit, but you haven't put it in the running sum until you get to this line. So if 9 says, oh, only the first element is good, you've only read. Does reading cause damage?
No.
Well, actually, segmentation. If you go over a segmentation,
Okay.
yes, segment fault. But that's about the only danger you have, is if you get a hardware segment fault. If you're within the same block, you've loaded the block at a time, then no, you can't get a problem with the read. So assuming we haven't done that, this one will prevent these from happening, as long as you check it. This one will prevent this one from happening as an exit from A if it shouldn't have been read. So it can be safe. Now the question is, obviously I can't keep reusing the R1s
Right.
for all of them. One of them has to be R1, and one has to be, what did I go, R9. One has to be 10, and one has to be 11.
How many registers do we have?
32.
Okay. So, well, my whole thing was if we just, because we don't want to use, if we change R1, we can't have R1 top there because we want to go through all 3 before we go back to the top.
Okay, so let me ask you. You've heard the 2 arguments. One of them is the right answer. Who goes with 8?
So,
Who goes with 8B?
the rest?
5. I have always wanted to meet ghosts. There are illusions. There are people who look like they are here and are not. Right? You should vote. One of them. Let's try it. Who goes for 8? Look how I call you guys.
That's
Okay,
right.
now we got some people. 1, 2, 3, 4, 5, 6. People have teleported in. Okay, Avi's behind, but there's one chance to make it back up. Who goes with 8B? Oh, Avi pulls ahead again. She pulls ahead even higher. The reason is this: you're moving a block at a time.
Right.
If this is the one that's updating R1, next block around, this is where it's pointing as an index. So everybody else will be counting 1, 2, 3. And they should be going from here. 1, 2. You've got to move the entire block. The second I go to block, your index is a block. And then you have to do offsets inside the index. So R1 is counting the block. It must move a block. So that's why it's there. Now the reason why I want you all to vote again is until you've done it, if you were wrong, you'd be like, right? It'll trigger the things to make you start learning. If you got it right, funny thing is, you know, if you knew why, you were okay. If you weren't, yeah, not so much learning. Hell, I guessed it right anyway. Strangely enough, those who get it wrong tend to learn faster.
So was my argument kind of valid?
You were close, you just didn't, I knew what you were saying, you have to jump up to the top, that is the block.
Right.
But you didn't state it clearly, so nobody knew what you were saying. I think if most people got the thing of, hey, you're moving a whole block, you probably would have persuaded more people. Which is why it's important not just to be right, but to know why you're right. There have been times when I worked in industry where somebody was right and they couldn't convince anybody. And so people did the wrong thing. That's really damn frustrating.
Right.
Okay? Even for the other people later on down the line. So, in any case, 8 is going to lose. So we'll have 8, we'll have 8A, and we'll have 8B. And they all have to be add i's. And it'll be -1, -2, -3. And this one will get R1, and the other ones won't. So we had 9 and 10 available, if I remember correct. So now we've got all of our block offsets. Okay? Which means I can stick them anywhere I want. So I can go 8, 8A, 8B. Now technically these spots here, since I did that, this thing, I didn't have to schedule a 6A, a 6B, a 7A, a 7B, so there's 4 spots that didn't have to get spots. They technically have no option, which means I could actually unroll again and try to stick some more stuff in. Because if I do that, I've got 4 here, I add 1 more line, which will add 3, that gives me 7 blank spots. 7 blank spots is sufficient to hold a whole nother iteration. Because it's 9, but I don't have to do 6 and 7. I just make my blocks equal to -16. So I only have to have 7 commands. So if I unroll this 4 times, even with the efficiency, I can make it go. But we'll just stick with this one for a moment. Technically, I did the equivalent of 27 commands. Right? Because I originally had 9, I've done 3. So I did the equivalent of 27 commands that was going on. How many cycles? 5, 6, 7, 8, 9. Right?
Right.
So my old time was would have been 27. My new time is 9.
So you have a speed
For
up of
this.
3.
So I have a speed up of 3, which is an ideal speed up. But I've got a really weird case. I got the ideal speed up, but what's my efficiency?
It's not. It's you have 4 no offs, so it's 23 out of 7. Yeah.
But so I got ideal speed up, but I don't have perfect efficiency.
That's great for real time, right?
Well, it's actually, this is quite good in many cases, because I could actually, if I went to 1 extra level, a 4th unroll,
Right.
because I could put in, you know, in here I'd have to load the other thing, but I can move the 6 down, and I can do a 1B, 2B, or sorry, a 1C, 2C, and that's why I move 6 out of the way. And then I wait a couple cycles, and I can
So we'd have.
load it in, and I can multiply and all the rest of that stuff, and I can just interleave them. So I can stick that one in. So I should actually be able to get
30.
4 of them in 10,
Right.
which is 4 times 9, 36. I can get 36 over 10, which means I'll get a speed up of 3.6 and an efficiency of 100, when I should have only got a speed up of 3, because I did a little bit there. So I can actually beat your best by a little bit.
So on the test.
I would not expect you to do this on a test.
Okay.
If you did this on a test, I'd go, wow, that's awesome, they learned it, then I'd probably give you some extra for it.
Perfect.
So for the
Keep in
no-ops,
mind.
is there any sort of argument we can make for power efficiency, since you don't have to run that process?
Keep in mind, I might be able to do it.
Clock cycle, or does that not really apply, because you're still up?
It's,
That's
but
why
you're
we're
not
gonna study
actually
this
turning that
weekend.
one off, because it is calculating.
That's why we're gonna
stuff
study
like
this
that
weekend.
cycle. I mean, theoretically, the no-op that's going in there is gonna, go through and be using something, because you're still calculating, it's got
Yeah.
0 plus 0, which means it's gonna be clearing the bits.
Public?
And the bits before have been something else, so you're gonna be discharging the bits, and it's power to discharge the bits. Probably not.
We're gonna study Saturday night probably,
Power.
because I have to go to Orange County in the
It's a good question.
We
mid-afternoon.
might meet up before then, though. Before
We good?
you come. Like, I'm just gonna go over to Taylor's in the morning.
I can do the morning too.
Morning?
Yeah, I'm gonna find out tonight what time.